We had enough of conversions, mass and moles. It's time to differentiate molecular and empirical formula. Molecular formula is complete in a sense that it gives you the type of atoms and their corresponding number in a compound structure. It allows us to decipher the formula of a compound based on its structure and vice versa. That is why molecular formula is important in studying chemical bonding. C2H6 is the molecular formula for ethane. It is a flammable gas with two carbon atoms in its structure. It is saturated since each carbon atom is bonded with the maximum number of hydrogen atoms it can possibly hold. The structure is in accordance with the molecular formulas you can notice. On the other hand, the empirical formula tells us the simplest ratio of elements in a compound. CH3 is the empirical formula for ethane. In ethane, the ratio of carbon to hydrogen is 2:6, which can be simplified as 1:3, thus CH3. If the ratio of the elements in a compound given by the molecular formula cannot be simplified anymore, then the empirical formula will be the same as the molecular. The ratios hold true on the molecular level. Actually, we have employed this idea earlier. Let me show it again to you. From the formula CO2, we can infer that in a molecule of carbon dioxide, there is a carbon atom and two oxygen atoms. Therefore, if there is 1 carbon per 2 oxygen, there is also 1 mole carbon per 2 mole oxygen in a mole of carbon dioxide, thus the conversion factor. Lastly, we must take note that if the molar amount of each element in a compound is known, we can use the data to decipher the empirical formula and vice versa. Let's have an example. This is a complex one, but don't worry, I will explain it the most basic way possible. Determine the empirical and molecular formula for chrysotile asbestos if it has the following percent composition: 1.16% hydrogen, 21.60% silicon, 28.03% magnesium, and 49.21% oxygen. The molar mass of chrysotile is 520.8 grams per mole. We can imagine percent composition like a pie chart. It tells us the ratio of the constituent elements in a compound. We can see here which is the least and the most abundant. We have discussed earlier that given the molar amount of each element in a compound, the empirical formula can be determined. But this idea can't be directly applied in this problem because we are given the percent composition rather than the molar amount. So we must find a way to use the percent composition data to be able to get the molar amount. This kind of problem is usually solved using the following steps. So there are 5. Let's start with an assumption. We assume that we are dealing with 100 grams substance. The value is arbitrary. You can choose 1000 grams, 500 grams, but in this case we will use 100 grams because it will simplify the calculations. Having assumed that we are dealing with 100 grams of chrysotile asbestos, we can use the percent composition to determine the mass of each element. For the mass of hydrogen, we know from the percent composition that the compound is composed of 1.16% hydrogen. Therefore, if we are dealing with 100 grams substance, we have 1.16 grams hydrogen. For silicon, it's 21.60 grams. For magnesium, it's 28.03 grams. And for the oxygen, it's 49.21 grams. Now we can convert these masses into moles to be able to get the empirical formula. So the moles of hydrogen, let's start with 1.16 grams times the molar mass. Grams will cancel. We simplify that, we get 1.150908 mole. Next, For the number of moles of silicon, 21.60 divided by 28.08 grams, that is 0.769231 moles. For the number of moles of magnesium, that is 1.153023 moles. For oxygen, that is 3.075625 moles. So for the fourth step, divide by the smallest value. The number of moles of silicon is the least among the constituent elements of the given compound. Therefore, we will divide everything by the number of moles of silicon. So substitute the values. We simplify that, we get for the number of moles of silicon, that is simply 1. For hydrogen, that is 1.4962, simply 1.5. For magnesium, it is 1.4989, simply 1.5 as well. For oxygen, that is 3.9983, simply 4. These values will serve as the subscripts of the individual elements in the empirical formula. We need to ensure that the subscripts are whole numbers. So we will find a way to make sure that 1.5 will become a whole number. So we basically need to multiply everything by 2, because multiplying 1.5 by 2, we will get 3, which is a whole number. So 1 times 2, 1.5 times 2, and 4 times 2. That is 2338. Therefore, our empirical formula is Mg3Si2H3O8. For the last step, we will use the equation. The mass from the molecular formula is equivalent to a constant times the mass from the empirical formula. We are given already the mass from the molecular formula, that is 520.8 grams. Now we will calculate the mass from the empirical formula. Just get the atomic weight of each element times the subscript. This is simply 260.1137 grams. We substitute this to our equation. We get this. Now we can solve for C. Divide both sides by 260.1137 grams. We simplify this, we get 2. Therefore, the constant is 2. If the mass of the molecular formula is equivalent to a constant times the mass of the empirical formula, then molecular formula is the same as the constant times the empirical formula. So we will multiply the constant to our empirical formula. So the molecular formula is 2 times the empirical formula. Here we are multiplying the constant to the subscripts. So we get Mg6, Si4, H6, and O16. This is the molecular formula.